Hello and welcome everybody and welcome to Advent of Code 2022 day 9. Um so the difficulty we have established has definitely stepped up. Yesterday's problem wasn't too difficult, but today's problem for me there was a big step up in difficulty here. I don't know if it was me failing to think about the problem in the right way, but this one took me quite a long time to solve. For the part 1 anyway, it took me a good bit of time to kind of work through it and figure out a solution. And then when I eventually got to the part 2, there was sort of like one gotcha that tripped me up for ages and I just couldn't get it to work. Once I figured out that gotcha, then it all penny dropped and I was able to get it working. But yeah, it's a little bit involved, it's a little bit complicated. So we're going to step through it. It might be a little bit hand wavy because my code's not super pretty and it's kind of dense. It's, yeah, a little bit abstract, but I'm going to try my best to describe the process around how the solution works rather than, every single line of code, which is kind of what I've done up to now. So I'll try and keep it as short as possible because I could just talk for hours about this one problem, I think. Okay, so the problem, day 9, rope bridge. Basically, we're crossing an old rope bridge, and as you're crossing this bridge, you start wondering if it's going to be safe for you to cross it, and instead of thinking about falling to the ground below, you come up with a simulation about like rope modeling, and yeah, they pull the plank length in, which is yeah, why not? Sure, why not? But basically, what we have is a string that is sort of, of unit length of 1. It's got a head and a tail. And what we're doing is we're simulating the way that string can move around on a grid. So the input to the puzzle is the head of the string moving up and down, left and right. And what we're trying to do is we're trying to model where the tail should move. So roughly speaking, the tail needs to follow the head around, but there's some specific rules of how the head and the tail need to interact. So they always have to be touching. They always have to be next to each other, either, in a cross shape or in an X shape. So side to side, up and down, and then diagonally as well. But the way in which it moves around has a slight nuance. So the really simple thing for this would be that every time the head moves by 1 unit, the tail moves to the old position that the head was in, and it just follows it all around. That'd be really simple. But unfortunately, it's not quite as simple as that. So what can happen is, as the head moves around, there's a specific position that it gets itself into where the tail makes a diagonal jump to the next position that it has to be in so that it's always following the head. So that's, where can I see the example for that? Is there an example here? Yeah, so I think you can see it here. Yeah, so this is the idea. So what's happened is we've ended up in a state like this where H is here, the head is here, and the tail is here. They're diagonally opposite each other. The head's going to move 1 position to the right. So if the head moves 1 position to the right, the tail needs to move. Basically, the tail needs to move that way. It needs to jump from there to there. So it needs to make this diagonal hop across that way. Now, how exactly it does that, that's what we have to solve. The output then, what you're asked to do, the input is you're given these lists of directions. So the first thing is the direction. The second is how many places it's going to move in that direction. This is just for the head. So what you have to do is you have to simulate, you have to run through all of these movements, and you need to keep track of the tail as it moves. So if we scroll down, they give you, this is like the output that you get. So you have to keep track of the tail as it moves around. And then what they want out of it is the number of unique coordinates that the tail has ended up in as it moves through its pattern. So if that doesn't make a lot of sense, it's a little bit tricky to conceptualize what's happening. But yeah, let me jump into the code and we'll see if we can make some more sense of this. So we'll ignore this for now. There's basically you're operating within a grid, so I'm initializing a grid. The grid for the sample space is quite small. The grid for the actual solution needs to be much bigger. So I just flip between them instead of just making a massive grid for no reason for the sample. It's also, I can print the small grid onto the screen for debugging, which is what I was doing with the sample. So that's just why I have the different sizes here. Not hugely important. I create the grid. I make a 2D array. You don't really have to do this, but I did it because it made it easy to then print it out onto the screen as I was debugging it to figure that out, to figure out the solution. And for the way I've decided to start this is that I have a head and a tail in X and Y coordinate basically, which is the indexes for them. And I start them both on the very center of my grid. So if my grid is, a 20 by 20 grid, I'm starting at the point 10, 10 as my origin. I had previously started at the point 0, 0, but I realized that there's nothing to stop immediately moving to the left, say, on your input, and then you'd go into negative indexes in the array, and then things would just get convoluted. So instead, I just shifted everything into an arbitrary sort of index space in the middle. Doesn't really matter because you're gonna the grid's totally arbitrary. I just worked it out by trial and error. If I got an index out of bounds, I just increased the size of the grid, and then eventually I found some grid parameters pretty quickly that it was able to contain the entire solution. Okay, so the bones of the solution. You want to iterate through every single line in the file. For each line, you want to extract out what the distance is or which direction the head is going to move, and the distance the distance that it's going to move in that. So in my case, I figured, well, the distance is, say, it's going to move one step, right? And it'll do that 4 times. So if it's moving to the left, it'll go 1, 2, 3, 4 times to the left, and that'll be your amount of steps. So I set up an inner loop here, which will replicate the amount of steps based on that number. And then inside that, I just have a case statement in here, like a switch statement basically, which can figure out each direction and then adjust the coordinates of the X and Y coordinates of the head accordingly. So there's no diagonal movements. It's only up, down, left, right, which simplifies things a bit. So you just have 4 differences here. Left and right, they'll increment or decrement the X position, and then up and down, increment and decrement the Y position. So where really you get the guts of the actual problem the solution is in this update tail method. So effectively what this does is it takes the current tail coordinates, the current head coordinates, and it gives you new tail coordinates out of that. So that's what that does. I'll get into this in a second. So we'll assume that just works. It gives us a new tail coordinates. Then I'm updating the grid to set the new tail coordinates, the new head and the new tail position. I also back here at the very start, before I start this, I wipe those positions. So I say that to try and match this sort of output, I set a dot to be every coordinate, and then where the tail was, I set a hash in just so that it is visually kind of matches what you see, so it's easier to debug. Again, you can do this without it. You can get rid of all that stuff. I just left it in. So then once you've got your new tail coordinates, I have a hash up the top here, which basically is just keyed with the XY coordinates. And I have a counter in here that I can increment for the amount of times I land on that. I thought that might be useful in the second part. Turned out it wasn't useful in the second part at all. But basically, the length of that, the length of this visited hash for each XY coordinate that the tail landed in is the answer, the size of that. So because it's a hash, it doesn't matter how many times I put something into it, it's always just going to be constant. So, and you're told that it's the amount of unique positions, the amount of unique coordinates that your tail ends up in is what your output is meant to be. So there we go. That gives it to us. Now, the scary bit. So this is my update tail method, which is a little bit nuts, but It's just some maths basically and figuring out some translations. So I'll go through it quickly. It's not super difficult. Basically, I get two values. So if I have the two sets of points, the head and the tail points, I can figure out the distance between them, and I can figure out the slope, which is basically the angle that they're at relative to each other. So I chose to use the Manhattan distance, which is, if you've not seen it, this is like how you figure out the distance between 2 points on a grid, taking into account it's basically the sum of all of the x distances between them and the sum of all the y distances, and we call that the Manhattan distance between them. So it's almost like, it's like if you're walking blocks in a city, you just count the amount of times you walked right and up and right and up, and you get the absolute values of those and you add them together to give you those distances. Then the slope, you work that out by getting the angle. Basically, it's just the angle that they're at. So this is just a common formula for the slope. Take the difference in the y's over the difference in the x's. That's your answer. Now, I do an early exit here in the case where the distance is either 1 or less than 1. So whether that's the head and the tail are on top of each other or they're right beside each other, you don't need to do anything. And I also assume in this case that these slope things as well, they'll become more apparent in a second when I explain what the slopes actually mean in each case. So slope of 0 is they're side to side from each other. So they're either, it's like they're beside each other in this orientation. So x is here, and then the tail is either here or the tail is here. The head and the tail are in that same line. So that's one set of slopes. And in those cases, you just need to know where to move the x coordinate next, because you know that you're just moving, either you need to move towards the head or you need to go like back away. And you do that by knowing what that is, knowing that the slope is 0 and knowing that the x of the head is greater than the tail x coordinate. This is not easy to talk through. And then the next case underneath here, this is infinity and minus infinity, because those are things in Ruby. So this is basically vertical. So this is if the head is directly above the tail or vice versa. Now the next two are a little bit more abstract. These are the diagonals. So you've got okay, why is this so hard to describe? Effectively, these are angles that matter for the diagonals. I'm not going to go into them again, but there's two sets. There's the conjugate of each one. So there's this diagonal, and then there's this diagonal, and then there's also the positive side of that diagonal and the negative side of the same diagonal. Yeah, this is how that works out. This is the pattern that you apply, and it works. Trust me, it took me long enough to figure it out. So yeah, that's my part 1 solution. It's a little bit grim, but it gets the job done. Took me a while to figure it out, but we got there. So move on to part 2. Quickly, I'll kind of just run through this one. So basically what they changed the problem here, and instead of it just being a head and a tail stuck together following each other around, now it's a rope of arbitrary length. They say that the length is 10 in this case, so you start at basically the same point, and as you move, you end up with, where's the rope? The big example they have down here. Yeah, you end up with things like this. So you've got the head marked out, and then you've got the numbers 1 to 9. 9 is now the new tail section for it. And the rules are the same. So each piece of the rope follows the next one in the same pattern as the tail and the head. So if you modularly solved that solution, you can reuse that. So I'm thankful that I initially wrote this horrific function, the update tail function, because I can modularly reuse that for this one. So that's good. There's just one slight subtlety in how that makes it a bit different. So if we go to my code for my part 2, it's basically all the same, except instead, where here I have 2 sets of variables for the x and y coordinates for the head and the tail, instead I now have an array, or I used a hash here just because it's easier to index into for the specific character that I want, but it's effectively a list of the X and Y coordinates for 10 different points, which make up the entire rope string, whatever we're saying here. And then essentially the loop here is the same. It's just every time I would previously have been accessing one of the variables, I'm now indexing into this list of points. And the main key thing here is that I update the head position the same way that I would previously, except now I have a loop from 1 to 9, which iterates through the remaining 9 points and computes this update tail for each one in order, replacing the head for the next iteration is the tail from the last iteration, and it just does that over and over again, and it's able to compute each position in a row. And it's the same thing. We want to look at the very last one, and we want to record the position of the very last one with the same kind of hash that we did last time. So we have that here. It's position 9 we're interested in, and we record those values. The key difference here, and I think it's the only thing, and he kind of warns you about it. He calls it out here. He says, where is it? Be careful. There are more types of motions possible than before. And that stuck with me, but I couldn't see what it was, and that's what really, had my head messed up for a while. I couldn't see what the different position was until I eventually started printing out all of the distances and slopes that were coming up in the solution, and I figured out which one I was missing. And I was basically missing a 45-degree jump of like 2 sort of units in diagonal, which can only happen now that, it's only possible now because you can have your top one can be pulled diagonally away from that one, and now you have an extra gap in the middle that you need to be able to jump. And that I take care of here. It's a slope of 1 or a slope of -1, and the Manhattan distance will be 4. So up to now we did have a slope of 1 and -1, but they were only ever adjacent to each other. So that meant that they were already beside each other, so you didn't ever have to do anything in that case. But now the case is possible so in that case the slope was 1 and the Manhattan distance was 2, so you never had to do anything. In this case now, the slope is 1, the Manhattan distance is 4, so you need to jump in a diagonal. And you only need to do it when the distance is 4. If the distance is 2, you don't do anything. So I was doing that, and that was then breaking, and I was getting even more confused, and then I twigged that it was that Manhattan distance. So that's it. That's my whole solution. They both work. Input 1, that runs reasonably fast. Input 2 does not run reasonably fast. Well, I mean, it does still, but it's a lot slower, a lot more convoluted. I'm sure I missed some trick here. I don't think you had to do all this maths, but this is just kind of my default way of thinking, is to jump straight into sort of a mathematical solution to it, try and implement that. Sure, there was a cleverer, more algorithmic way to do it, but I didn't do it. So, so far, the hardest problem so far, I think. Didn't really enjoy solving this very much, I have to admit. But anyway, I hope you guys enjoyed the video, and I hope you had better luck solving this problem than I did. And if you were struggling with it, I hope I gave you a different perspective on it that maybe was helpful to you. Anyway, I will see you guys tomorrow for day 10. Hopefully it's not nearly as bad. See you guys.